Okay, very good morning. In the last class, we have completed the general process of Shannon-Fano encoding technique, and actually I have explained the example for m is equal to 2 bits per letter, where we have considered m as 2, that is the partition value is considered as 2. So you have partitioned the whole set into 2 subsets. And I asked you to solve the example, the same example, using m is equal to 3 bits per letter. And what happens whenever as m increases, as the number of value increases, what happens to the overall efficiency of our Shannon-Fano encoding process? Okay, that's actually I have given you as homework. I think at least a few of you have tried for that. Did any one of you tried for that? So can any one of you tell me what is the efficiency when if you increase the value of partitioning, what happens to the efficiency of Shannon-Fano encoding process? So any one of you completed or not? So anyhow, I will explain because this is also an important example. So here let us consider m is equal to 3 bits per letter. Please assign, so during the partition value m is equal to 3, please assign -1, 0 and +1 to the first, second and third groups respectively. So whenever m is 2, what we have done? So whenever m is 2, we have partitioned by using 2 subsets. So a complete set is partitioned into 2 subsets, and we have assigned like 0 to the upper subset and 1 to the lower subset. So whenever m is equal to 3, we have to partition it into 3 subsets. So for example, as the number of partitioning value increases, you have to assign it like you have to partition into more number of subgroups, and you have to assign to 4 bits accordingly. Here we consider the 3 bits as -1, 0 and +1. For the partitioning value, 3 bits per letter. Okay, so and you are asked to identify the change in the efficiency using Shannon-Fano encoding process. Here, please let us go through the same question which we have discussed in the last class. So I considered the same example, but instead of taking the partition value as 2, we are considering the partition value as 3 bits per letter. And what I told to you, so first thing is please verify whether all the given probabilities are in the decreasing order or not. If it is in the decreasing order, directly you can mention in the table. If it is not in the decreasing order, you have to keep it in the decreasing order, and accordingly you should represent the order of symbols. Which order? In the order of decreasing probabilities. So accordingly, you should list out the symbols with their respective probabilities in the decreasing order. And you need to construct the Shannon-Fano code for this, and also the efficiency. In the last class, we discussed that the efficiency of this encoding process can be evaluated by considering the average code word length, that is capital L. Once the table is constructed, you need to calculate the average code word length, and the second thing is you need to calculate the entropy. So there won't be any change in the entropy even if you consider m value as 2 or 3. So whatever may be the partition value, there will not be any change in the entropy, because entropy completely relies on the probability. So here there is the probability is fixed as usual. So whether the partitioning value may be 2 or 3, but entropy remains same because it depends on only the probability. Minus summation k is equal to 1 to n pk log p suffix k base 2. So it relies only on the probability. So the only parameter that it will change is the average code word length capital L, because this average code word length depends on the length of each code word. And the length of each code word once again depends on the type of partitioning. Okay, so that's why the average code word length will differ, and thereby it affects the coding efficiency. but remember that there won't be any change in the entropy. Okay, so first let us please ensure that all the probabilities are in the decreasing order. Next, please follow the steps given in the given below to obtain the Shannon-Fano code. So these three steps are remain same, except that we have to assign -1, 0, 1 to the 3 encoding bits. Okay, so let us go through the directly we can move to the table. So what is the first what is the first thing that you should do? Represent the symbols in the order of decreasing probabilities, because x1 to x5 they are as usual in the decreasing order. Directly we mention the symbols as well as its probability. Okay, next here m value is given as 3. That is, you have to partition the whole set. The whole set consists of x1, x2, x3, x4, x5. So this whole set is partitioned into three subsets, such that the probabilities are approximately equal or exactly equal. Okay, so here if you observe the whole set, we can partition x1 as one single subset and x2, x3. If you add, you will get 0.35 and here you will get 0.25. So we can partition as approximately equal probable case. Okay, so I have partitioned x1 as one subset, x2, x3 as other, and x4, x5 as third subset. So first subset consists of x1 element, second subset consists of x2, x3, and third subset consists of x4 and x5. Based on that, we'll partition the whole set into three subsets. So first subset, if you observe, it consists of only x1 element, and the second subset consists of x2, x3 element, and third subset consists of x4, x5. And after this partitioning, what is the next thing? Please assign the corresponding bits. Okay, so assign -1 to the first subset, 0 to the second subset, that is x2, x3, is 0 better. Next 1 to the third subset, that is x4, x5. So up to this it's okay. So we have divided the whole set into three subsets and assigned -1 to the first subset, 0 to the second subset, and 1 to the third subset. So here two partitions. This is so we have partitioned into three subsets. So by using two divisions. So -1, 0, and 1 assigned. Okay. Next, coming to the next part, further partition. Let us see, is there any further partitioning applicable to the given example or not? Now, if you observe the first subset, it consists of only single element. So there is no need to divide it or partition it further. So we can stop the partition of the first subset here itself. Next, if you observe the second subset, please listen carefully here. If you observe the second subset, it consists of two elements only, but we have to partition it into three. So it's not possible. So that's why we'll partition into two subsets and assign -1, 0 to the respective subsets. There is no chance to assign 1 to the third subset because only two elements are present. Here only two elements are present in the second subset. So even if you can, there is only possibility that you can partition it into two subsets. And we can assign -1 to the x2 subset and 0 to the x3 subset. And there is no possibility of assigning 1 to the third subset because the second subset consists of only two elements. The same will happen for x4, x5 subset because the third subset also it consists of only two elements. But we have a possibility of partitioning it into three. But because there are only two elements, we can partition it into 2 and assign -1 0, -1 to the upper subset and 0 to the lower subset, because third further chance is not there because third element is not present. So please assign -1 to x4 subset and 0 to the x5 subset. Now if you observe all the subsets, x1 subset is completed, x2 subset consists of only one element, x3 also only one element, x4 one element, similarly x5 one element. So we can stop the further partitioning. Okay, next coming to the code word, representation of code word. I already told you, in order to represent the code word for a particular symbol, follow its path in the horizontal direction. If you observe x1 symbol, its code word representation is, it consists of only one bit, that is -1. So directly I represented here. If you observe x2 subset, if you please follow the path in the same direction. So it x2 element consists of two elements, 0 and -1. Okay, and so I have represented the same code word here. Similarly, if you observe 0, -1, two bits are there. And if you observe x3, so partition 1, so it is 0, and partition 2 we have 0. So 0, 0. We can represent as 0, 0 as the code word for x3. And similarly, if you observe x4, the code word is 1, -1. So two bits are there, 1 and -1. And if you observe x5, 1 and 0. So 1, 0. Now let us represent the code word length, because we need to calculate the average code word length to evaluate the efficiency. So for x1, the length is 1, and for x2, the length is 0, -1. So it is 2 bits. So that's why I have represented 2. And for x3, the code word is 0, 0. So its length will be 2. And for x4, the code word is 1, -1. So its length is 2. And for x5, the code word is 1, 0. So its length is 2. So we have represented the code word length for each and every symbol. What is the next thing? Next thing is to calculate the average code word length. You can obtain that. Already I told you what is the expression. Summation k is equal to 1 to 5 p suffix k into l suffix k. So add all the products of probabilities and corresponding code word lengths. Okay, so 0.4 into 1 plus 0.19 into 2 plus 0.16 into 2 plus 0.14 into 2 plus 0.11 into 2. This is how we can calculate the average code word length. You can see it in the next slide. So if you observe the average code word length, I said you the same expression. Summation k is equal to 1 to 5 p suffix k into length of the corresponding message in bits. So you will get as 1.6 letters per symbol. But what about the entropy? Entropy remains same because entropy depends only on the probability. Here there is no change in the probability, so it remains same. So already we obtained the entropy as 2.15 bits per symbol. Okay, so let us calculate the code efficiency. So code efficiency is h of x, which is equal to L into h of x by L into log m base 2. Here you can see that h of x is as usual 2.15 వేస్తారు, and L is it's where changed to 1.6. So 1.6 into log m base 2. Here partition value is 3. So log 3 base 2. So it will be log 3 by log 2. So you will get it as 1.584. So please substitute 2.15 divided by 1.6 into 1.584 multiplied by 100 gives you the efficiency. So if you observe, the efficiency is 85.02. But what is the efficiency if you take the partition value as 2? Let us move to the corresponding slide. Actually, here, please observe this slide. If you consider the partition value as 2, we obtain the efficiency as 95.5%. 95.5%. But if you observe the partition increase in the partition value as 3, then what happens to the efficiency? It is 85.5%. Almost all there is a reduction of 10% efficiency if there is a single value increase in partitioning. So as the partition value increases from 2 to 3, there is a decrease in the efficiency by 10%. So this is because the denominator becomes log 3 base 2. Instead of log 2 base 2, we'll get log 3 base 2. So what is the conclusion that you can say here? As and when the partition value increases in the Shannon-Fano coding method, the efficiency will reduce a lot. So it reduces by a factor of 10% in this example. So that is the conclusion. So you can already check also identify the change in the efficiency using the Shannon-Fano coding. As the partition value increases from 2 to 3, in this case, the efficiency reduces by a factor of 10%. Okay, so you need to conclude like that. So that's why I mentioned here the main drawback of, in the drawbacks I mentioned you that as m increases, as m tends to increase, this method is not suitable for m is equal to 3 bits per letter. Okay, why it's not suitable? Because as m increases, the efficiency will reduce. Efficiency of the coding technique will reduce. And already I told you these drawbacks in the last class. So here we have multiple ways of partitioning. So efficiency is not stable. And here every time some code word will be the prefix of other code word. So if there is any error or loss, that will be propagated. So we have to verify it from the starting onwards. Okay. So if there exists any error, we have to verify it from the beginning. So also it doesn't guarantee optimal codes because it uses a cumulative distributive function. Okay, and that is the reason that it produces low efficiency, and even when m tends to increase, still the efficiency will reduce. So for this method especially, reduction value is better only if you consider m as 2 instead of increase in the partitioning value. Okay, so let us go to the Huffman coding. So I told you the advantages of Huffman coding. So it follows the lossless compression technique and entropy based source encoding process. So that's why that is the common advantage for both the Shannon-Fano and Huffman coding. And in Huffman coding, no code word is a prefix of other code word. No code word is a prefix of other code word. So there is an ambiguity in the Huffman coding. So you cannot find this kind of ambiguity in Huffman coding because here it doesn't follow the partitioning process. It completely relies on the process of combining. Huffman coding do not rely on the process of partitioning. It completely depends on the process of combining. So here last two terms will be combined. Okay, last two terms will be combined. It is instead of partitioning, here we'll combine the last two terms or last three terms based on the combining factor. Here M is the combining factor, and in the case of Shannon-Fano coding method, M is the reduction factor, or you can say partitioning value. M is the partitioning value in the case of Shannon-Fano coding process, and here M is the combining factor. So whenever M is 2, last two terms will be combined, and whenever M is 3, here M is the combining factor. M is 3, last three terms will be combined. But similar to the Shannon-Fano, this process is also an entropy-based source encoding technique. Here already I told you that no code word will be the prefix of other. So even though there exists any error, it's enough to consider only the corresponding effect of symbol instead of considering all the process from the beginning. So the corresponding symbol effect is enough to consider. And here this uses prefix precodes. So that's why there is a possibility of getting the lowest possible code word length. So in the case of Shannon-Fano coding method, because it uses cumulative distributive function, so we cannot be able to reduce the code word length, average code word length. But in the case of Huffman coding, as it uses prefix precodes, we can be able to reduce the code word length. What happens whenever the code word length reduces? Efficiency will increase, because efficiency eta is equal to h of x by L bar multiplied by log m base 2. So because L is in the denominator, as L decreases, our efficiency eta will increase. And in this case, especially Huffman coding, as m tends to increase, the reduction process will last with a low span of time. Here also there may be effect on the efficiency, but the reduction process we can complete it within a low span of time, because we'll combine the last three terms. So if you add up like last three terms, so that you can finish the reduction process or combining process within a short span of time. Okay, these are all the advantages of Huffman coding. Let us move to the example. And here I mentioned you the procedure. See here it is efficient because it uses the prefix precodes, because no code word will form as a prefix to the other code word, because here we will just combine the last three terms. So once you partition, you will assign the bits to the assign the values to our corresponding subsets. So therefore there may be a possibility that one code word will act as a suffix to the prefix to the other code word, but here there is no problem like that, because it relies on the process of combining. So what is the step 1 here? Step 1 is represent the symbols set in the order of non-increasing probabilities. So let us represent the symbol set in the order of non-increasing probability. So this step 1 is common to both Shannon-Fano as well as Huffman coding. What is the step 2? Here we'll combine the last two terms. Instead of partitioning it, partition the subset into two subsets. Here we'll combine the last two terms. In Huffman coding, the last two terms or last three terms are combined based on the value of combining factor capital M. Okay, so if last two terms are combined, we'll assign 0 to the last term and 1 to the last but one term. Okay, so we'll assign 0 to the last but one term and 1 to the last term respectively. Okay, and for example, if M is 3, combining factor is 3, then assign, okay, then assign -1 to the last but one second term and 0 to the last but one term and 1 to the last term. And once you assign like that, and after combining, Once again, this added probability will be represented in the non-increasing probabilities. So this combining process, assigning, and what is the next step? This next step is representation of all the probabilities in the non-increasing order. So every time the probabilities will be represented in the decreasing order. Okay, next step 3 is the reduction process will continue. See here, reduction process or combining process. So here you can write it as a reduction process or combining process. So the combining process, the reduction process or combining process will continue in the same manner till m number of messages remain in the reduction. So for example, if m is 2, the same process will continue till 2 messages remain in the reduction. So after completion of this whole combining process, we can construct the Huffman coding table. We can construct the Huffman coding table, and in the same manner what you did, we need to represent the code word for each and every symbol, and then we will calculate the average code word length, entropy, and finally the efficiency. So entropy definition is remains same. It relies only on the given probability. And average code word length depends on the code word length of individual symbols. And efficiency depends on entropy, length, average code word length, and that maximum efficiency, that is log m base 2. So here there is no problem of ambiguity, because here we follow the combining procedure or reduction procedure instead of partitioning. So we can see that there is an increase in the Huffman coding approach instead of Shannon-Fano coding technique. Okay, these are the corresponding steps. Please remember, first step is represent the symbol set in the non-increasing probability. This is the same as Shannon-Fano. And second step is last m terms are combined. M probabilities are combined, and we'll assign, if for example, if m is 2, we'll assign 0 to the last but one term and 1 to the last term. And once again, after assigning, once again these probabilities are represented in the non-increasing order along with this newly added value. So if it will add chesaka, you will get one probability. That probability is once again represented in the order, decreasing order. So, and the step 3 is this process will continue in the same manner. So it a process combining, assigning, and once again representing it in the decreasing order. This process will continue in the same manner till m messages remain in the reduction. Okay, next we'll calculate the efficiency. So let us move to the example. So please listen carefully. This Huffman coding table construction is very important. So once you know the procedure, you can easily solve any kind of problem. So ఈ మోడల్ తప్పించి ఇక మోడల్ మార్చడానికి ఏం లేదు. You will get either Shannon-Fano coding method or Huffman coding. So out of these two, you will get one question from the during your external exams. So a discrete memoryless source has an alphabet of 7 symbols. With probabilities for its output as described in the table. Okay, so take m is equal to 2 bits per letter. Take m is equal to 2 bits per letter. So here they have given you the reduction value or the combining factor as 2. So that's why during this reduction process or combining process, you have to combine the last 2 terms. Okay, last 2 terms, and assign 0 to the last but one term and 1 to the last term. Okay. Now please observe the symbols. So the values symbols are given as S0, S1, S2, S3, S4, S5 and S6. So a total of 7 symbols are there starting from S0 to S6. Next, please observe the probabilities. The probabilities are given as 0.25, 0.25, 0.125, 0.125, 0.125 and 0.0625, 0.0625. Now, while calculation of entropy, if you want to represent these probabilities in the factor, you can represent. So 0.25 you can represent as 1 by 4 and this is 1 by 8 and 0.0625 is 1 by 16. Okay. So probability, please represent all the probabilities in the decreasing order. If you observe the probabilities, S0 value is greater than and it is equal to S1 and if you move to S2, S3, S4, S5, S6, our probability is in the decreasing order only. So there is no need to reassign the symbol order because symbol order is it's okay. It's in the order of decreasing probability only. So there is no need to reassign the order of the symbols. So first ఇది మాత్రం మీరు ఖచ్చితంగా చెక్ చేసుకోవాలి. You should check the probability of the corresponding symbols or messages given in the question. See whether it is in the decreasing order or not. ఇక్కడ two points you need to consider. One is take the sum of all the values and check whether it is equal to 1 or not. If you add 0.0625 and 0.0625, you will get 0.125. If you add these four values, you will get 0.5 and S0, S1 gives you 0.5. Total is 1. So here whenever the question is given to you, please check the probabilities. So sum of all the probabilities 1 and second thing is, so second point is common for Shannon-Fano and Huffman. See whether the probabilities are in the decreasing order or not. If it is in the decreasing order, mention in the same order for construction of either Huffman coding table or Shannon-Fano coding table. So decreasing order unte same order use chestaru while constructing the Huffman coding table or Shannon-Fano coding table. If it is not, then you have to reassign the symbols. For example, if S2 has 0.25, then you should take S2 to the first position. So S2 0.25, next S0, S1, S3, S4, S5, S6 like that. So anyhow you need to represent in the decreasing order. So remember that. Okay, here you need to calculate the Huffman code. Okay, and you need to construct the Huffman code table for this source, moving the combined symbol as high as possible. Okay, so they asked you to continue the combining process or reduction process as high as possible. How far you can combine? Till m number of symbols are present in the reduction process. And they told you that in this example you will get the efficiency as 100% and why the efficiency is 100 that you need to tell. Okay, so you need to justify that why the efficiency is 100%. Okay, so let us go through the construction of Huffman coding table. So because the probabilities are in the decreasing order, you can represent in the same order S0 to S6. Let us move to the next slide. So here you can see the Huffman coding table. So this is how we'll represent the Huffman coding table. But in the case of Shannon-Fano, you know how to do. You will partition the whole set. S0 to S6 will partition. So ఇక్కడ partition చేస్తే ఎలా ఉంటుంది S0, S1 into one group and S2 to S6 into another group. But here the Huffman encoding process doesn't rely on the process of partitioning. It relies on the process of combining. And here combining factor or reduction factor is given as 2. So what you will do? First step is represent the symbols in the decreasing order probability. So check the probabilities. It is 0.25 to 0.0625. It is in the decreasing order only. So represent in the same order because they are already in the decreasing order probabilities. So S0, S1, S2, S3 up to so on, S6 వరకు represent చేశారు. Next, please represent the respective probabilities. As the second column, first column is symbol and the second column is the represent the same corresponding probabilities, and please mention here as stage 1. So what we'll do here, the last two terms are combined. So what you will do, in the case of Shannon-Fano coding, last Shannon-Fano coding will partition into two subsets, but here last two terms are combined because m is given as 2. If you combine these two, 0.0625 and 0.0625, you will get it as 0.125. 0.125. So please add the last two terms. You will add S5 and S6. If you add these two, 0.0625 and 0.0625. If you add, you will get 0.125. Okay. And after adding, what you will do? Please assign 0 to the last but one term. Here last but one term is symbol is S5. So assign 0 to the last but one term and 1 to the last term. Assign 0 to the last but one term and 1 to the last term. So after assigning, so I told you to combine, then assign. So combine the last two terms based on the value of m. If m is 3, last three terms are combined. Last three terms combine cheste, you will assign -1 to the last but second term and 0 to the last but one term and 1 to the last term. In this example, you will assign 0 to the last term, 1 to the last but one term. So these two are added. Okay, these two are added and you will get, and you are assigned 0 and 1. And the next is, in the step 2, what is the next thing? Relocate the corresponding combined probability in the decreasing order probabilities. Okay, so if once again we will rearrange all these probabilities in the decreasing order. But remember one point, while representing in the decreasing order, the thing that you should remember is, for example, if the combined value is equal to, if you have same values, some more values, like 0. Here you have 0.125. If you have the same value 0.125 already in the order, then you have to relocate ours to the highest position. So the newly combined value is added to the highest position if you have equal probability. And the old probabilities are represented down to the combined value. So the preference will be given to the combined factor. Okay, so if the, it should be represented in the decreasing order only. So the probabilities are once again rearranged in the decreasing order upon relocating this combined factor to the highest position if we have similar probability values. If we have similar probability values, take the combined factor to the highest position. But the order should be in the decreasing order. Okay, so 0.25, 0.25. Next we will get the combined factor, that is 0.125, and the same 0.125 is old ones are represented down to the newly combined factor. Okay, so okay, this is stage 2. Next in the stage 2, once again you will combine the last two terms, because this combining, assigning and once again relocating the probabilities in the decreasing order, this process will continue till the last reduction consists of two probabilities. Okay, the same order will continue till the last reduction process consists of 2 probabilities because here M is 2. If M is 3, the process will continue till the last stage consists of 3 probabilities. Okay, let us move to the step 2. So in the stage 2, what you will do? Once again, you will add 0 like 0.125 and 0.125. You will get it as 0.25. Now, please assign 0 and 1 to the 0 to the last but one term and 1 to the last term. After assigning, once again relocate this newly added probability in the order of decreasing probabilities. But here we got it as 0.25. Already we have 0.25s in the table, but these old ones are represented down to the newly added combined value. So that's why this is relocated to the first position. So please relocate to the in the order of decreasing probabilities. And if you have similar probabilities, please take consider those as the old ones and take this combined factor to the highest position. And it should be in the decreasing order only. So please mention it with the arrows so that you can identify the path of each and every symbol. At last, you need to identify the code word by using this path. So please represent the path clearly. Okay. So here first the stage 1 0.0625, 0.0625 are added. So 0 is assigned to S5 and 1 is assigned to S6. And the added term is moved to the position of S2 because already we have 0.125, so 3 0.125 probabilities and these are kept down to the combined value. Okay, please mention it with mention the direction with the arrow. Stage 2 once again 0.125 or 0.125 both are added. And this newly added value is moved to the top position because the value is 0.25. We have only maximum value as 0.25. So and we have already 2 values. So please take that values down to the combined value. So the combined value is 0.25 and these values are kept down to the old values are kept down to the newly added value. So 0.25, 0.25. Next, it is followed by already existing values, that is 0.125 and 0.125. Okay. Next, in the stage 3, once again last 2 terms are combined and assigned 0 to the last but one term and 1 to the last term. While while assigning and relocating the order of probabilities, please don't change the please observe the reduction process. During the first reduction, we'll have a reduction from S6 to S5 అంటే మీకు S5 వరకే బిట్స్ ఉండాలి. In the second reduction we will get S4 and in the third reduction you will get the bits up to S3 and in the fourth reduction you will get the bits up to S2 and in the fifth reduction you will get bits up to S1. Okay, so please observe the reduction process. This reduction process continue during combining. And once again in the stage 4, last 2 bits are combined. So 0.25 plus 0.25, how much it is? 0.5. So in the probabilities we don't have 0.5 here. So that's why this is the maximum value. So next, while representing in the decreasing order, our combined value goes to the highest position. And then followed by 0.25 and 0.25. Once again, last 2 terms are combined in the stage 5. Once you combine like that, what happens? You will get 0.5. But already we have 0.5 in the order. So that will be collected as the old one and a newly added factor will move to the top position. So while relocating the order of probabilities, it should be the decreasing order. For example, if the newly added value is same. Okay, if the newly added value is same to some of the probabilities, that probability, old probabilities will be kept down and the newly added will be moved to the higher position when we have similar probability values. So 0.5 will take to the higher position and the old one will be down to the new 0.5. So next, in the stage 6, if you observe, it consists of two probabilities, two symbols. Okay, so directly you can add these two and you will get 1. Okay, and then please assign 0 to the last but one term and 1 to the last term. Okay, like that, this combining process will continue and you can identify the reduction of one symbol in each and every step. Okay, you can observe a reduction in each and every step. So in the first stage, if you observe, okay, if you are observe the first stage, there is a reduction in one symbol. The stage 2, if you observe, we have reduced one symbol because we have combined last two terms. If you combine the three terms, if as you increase the value of m, for example, if you combine last three terms, what happens to the process of this reduction? We can complete it as early as possible because within a short span of time you can finish this reduction process. So what you need to do here? First, represent all the symbols in the decreasing order. And the second thing is, please combine the last m terms. In the question, m is given as 2. So last two terms are combined. And after combining, please identify that value and assign 0 to the last but one term and 1 to the last term. And the newly added value is taken to the in the order of decreasing probabilities. But for example, if you get the combined value as same to some of the probabilities, then take that combined value to the top position out of the similar probabilities, out of the existing similar probabilities. So 0.125, 0.125, 0.125 will be kept down. So if you are changing the position of symbol S2, please mention it with the arrow. Already ఇక్కడ S3 position మారింది. So mention it with arrow. S4 position, mention it with arrow. So this is to calculate the code word. So the direction of the varying probability, or you can say the direction of the corresponding symbol, the path should be identified clearly. Next, we combined 0.125 and 0.125 in stage 2. And if you see, this moves to the higher position, 0.25. So this 0.25 S0 will move down and S1 will also move down and S2 will move down, S3 will move down and S4, S5 already added. So there is no need to, already it is combined, it is moved to higher position. Like that, during combining, you will assign and change the position of combined order probability. Okay, and other probabilities, please mention it with the arrow. The directions, please mention it with the arrow. Okay, like that, this combining process, assigning process, and relocating the order of decreasing probabilities. If the combined value is similar to the already existing probabilities, please take this to the top position. Okay, and this process will continue till the reduction process consists of only two symbols or two probabilities. If m is 2, if m is 3, you need to get last 3 symbols. You should continue till last 3 symbols, and anyhow you need to assign with 0 and 1 when m is 2. When m is 3, you need to assign -1, 0 and 1 to the last terms, 3 terms. Okay, I think this is clear to you. Let us move to the calculation of code words. Let us see how you can calculate the code word. In the case of Shannon-Fano, directly you can observe the path in the forward direction. But here we need to identify the path of the corresponding symbol in the reverse direction. In the reverse direction. Already we mentioned the path of S0. Please observe the path of S0. it is 0.25, 0.25, and it is in stage 3 it is moved down, and stage 4 it's once again moved down, and stage 5 these two are combined and moved to 0.5, and once again in stage 6 it is moved one step down. Okay, and identify the assigned values. So please identify the assigned values in the reverse order following the path of the corresponding symbol. Follow the path of the corresponding symbol in the reverse direction to calculate the code word. Please remember this. The code word for Huffman encoding process of a particular symbol can be calculated by observing the path of the symbol in the reverse direction. Now let us see how we can calculate the code word for S0. If you observe the path of S0 in the reverse direction, first let us see the forward direction. Here it is moved to stage 3, it is moved down, stage 4 it is moved down, and stage 5 it is moved up, and the stage 6 it is moved second position. Now start from here. 1. Next for 0.5, did you assign any value? No. So next move back. So for 0.25 you assigned 0. So our code word is 1, 0, and nowhere we have assigned value. So what is the code word of S0? 1, 0. So if you observe the code word for S0, to calculate the code word for S0, please follow the path of the symbol in the reverse direction. So now I request any other student to please tell me the code word for S1. S1 path is from stage 1 to stage 2 no change. Ikkada ఏ change లేదు. Next stage 3 కి వచ్చేసరికి it has moved down. Stage 4 moved down but assigned with value 1. And this combined value is moved to stage 5. So no assigned value. And it is moved to 0.5. It has assigned value with a value of 1. So can any one of you tell me what is the code word for S1? See, please follow the path of S1. Okay, first you move in the forward direction and represent the code word in the reverse order. So if you observe S1, it is no assigned value. Here also no assigned value. Here you have assigned with 1. Next move to stage 5, no assigned value. Stage 6 you have assigned with 1. So now it is 1, 1. Write in the reverse order. So it is 1, 1. So what is the code word for S1? 1, 1. Let us calculate the code word for S2. I request any one of the student to please tell me what is the code word for S2. What is the code word for S2? Any one of you, please. Please follow the path of S2. Please follow the path of symbol S2 to calculate its code word and represent the code word in the reverse order. Can any one of you tell me what is the code word for S2? So here S2 0.125. Next it is moved here. It's 0.12. It's moved here. It stays 3, but it is assigned with a value of 1. Okay. So next it is moved to 0.25. Next 0.25. So you have 1, 0. Next 0. So what will be the code word for S2? Chapalamba, what is the code word for S2?
Zero, zero, one.
Okay, please wait. So what is S2? Here you have no change. So ikkada change ochindi. Next you have 0.125 you have assigned with 1. So it is moved here. Next it is moved here. So 0. Next it is moved to 0. Enta chepparama?
0, 0, 1.
0, 0, 1. Actually, if you follow the path of S2, you will get 100 code word, but you have to represent it in the reverse direction. So 001 is the code word for even. Very good. For S2. Ba, meer okkasari cheppandi, what is the code for S3? S3 code word. So here you have 0. Next, here no asset value, 0, 1. Next, it is 0. Can you tell me what is the code word for S3? S3 order చూడండి. Here in stage 1, it is in the 4th position. S2, it is in the 5th position. But here you have assigned value as 0. So write it somewhere 0. Next followed by 0.25. Here no assigned value, so no need to consider. So next it is moved down. Here also no assigned value. Next it is moved down. It is 1. Next it is moved up. So it is 0. So how much for S?
0, 1, 0.
0, 1, 0. Okay, very good. Now, can you tell me for S4? Can any other student? Can you tell me the code word for S4?
0, 1, 1.
For S4, it is. Please follow the path from 0.125 to 0.1. It is 1. Next, move it to stage 3. No value. So here also no value. Here it is 1. Here it is 0. ఎంత చెప్పారమ్మా 1 1 0 వచ్చింది. If you write it in the reverse direction, okay, 0 1 1. Okay, good. You only tell me what is the code word for S5. For S5, it is first asset value is 0, and here we relocated. Next, it is 0. Next row value. Next,
0,
it is
0,
0. 0 0
0, 0.
0 0. 4 zeros. Okay, very good. Next, if you want to check, you can move to the next slide. See here for S4 it is 0 1 1 as you said. For S5 it is 4 zeros. Okay. Next, can you tell me for S6? S6 ki cheppandi. This is the last one. 1
0, 0, 0, 1.
0 0. ఎంత చెప్పారు 0 0
0, 1.
Okay, 0 0 0 1. Okay, very good. So like that, so ee point మీరు రాసుకోవాలమ్మా. How can you calculate the code word for Huffman coding? So in this process, observe the path of the symbol in the forward direction. First observe the path of each and every symbol in the forward direction to calculate its corresponding code word. And please write it in the reverse order. మీరు మళ్ళీ రివర్స్ పాత్ ఐడెంటిఫై చేయడం అంటే కొంచెం ఇట్స్ ట్రబుల్ ఫర్ యూ. So better you follow the forward path of S0 or S1 or any symbol. So the code word, if you want, so the code word of a particular symbol can be calculated by following the path in the forward direction and write the code word in the reverse order. Okay, write the code word in the reverse order. So like that we can calculate the code words for each and every symbol. So it's don't write the code word directly in the symbol, or else you can directly write here. So after stage 6 you can write code word and then followed by length. Okay, so directly with table pakkad represent chesna, no problem. So there is no need to represent table like this. Directly you can continue the code word after all 6 stages. So we have certain number of stages. You can directly write the code word and its length directly in the Huffman chart, as what we did in the Shannon-Fano coding procedure. Now already we calculated the code words. Okay, can any one of you tell me the length? How can you calculate the length of each and every symbol based on the code word? How can you calculate the length? Any one of you, please tell me, how can you calculate the length? Amma, cheppandi.
Based on the number of bits present in the code word.
Based on the number of bits present in the code word. So for S0, if you observe, it has 2 bits. So directly we represented the length as 2 bits. And for S2, 2 bits. For S3, 3 bits are there, 0 0 1. So for S3, it is 3 bits. So directly you can write 3. For S4, it is also 3. For S5, it is 4 bits are there because 4 zeros are there. So 4 bit. So for S6 also we have 0001, so 4 bits. So like that you can calculate the code word length. Code word length for each and every symbol. So now from this onwards almost all the procedure is same because it is also an entropy based source encoding technique. Okay, so same equations you can use and first let us calculate the average code word length. So how can you calculate the average code word length? The probability multiplied by code word length. Take the sum of all the corresponding values for each and every symbol. So that is summation k is equal to 0 to sub 6 because we have 7 values. For example, మీకు S1 to S7 ఇచ్చారనుకోండి, then you will write it as k is equal to 1 to 7. Here it is given as 0 to 6, S0 to S6 or M0 to M6 అంటే summation some k is equal to 0 to 6 పెడతారు. అదే మీకు S1 to S7 ఇస్తే 1 to 7 అని పెట్టుకుంటారు summation. So summation k is equal to 0 to 6. Here k is a variable. P suffix k, that is the probability, multiplied by the corresponding length. So 0.25 plus into 2 plus 0.25 into 2 plus 0.125 into 3 and it is repeated thrice. So directly represented as into 3. Here 0.25 into 2 is repeated twice. And 0.125 into 3 is repeated thrice, that is for S2, S3 and S4. And 0.0625 is repeated twice and both consist of 4 bits. So that's why you can write directly 0.0625 into 4. It's repeated twice, same values are repeated twice. So finally we update the average code word length as 2.625 bits per symbol. 2.625 bits per symbol. So like that we can calculate the average code word length. So we update it as 2.6, how much? 2.625 you update. Now let us calculate the entropy. I think you are very much familiar in calculating the entropy because entropy is, you can write, if you want to write it as log 1 by p of xi, don't put negative sign, but if you write it as log p of xj, please mention summation, negative sign prior to the summation. So here they represented p of xj into log 1 by p of xj, so no need of minus negative sign. So summation I is equal to 0 to 6 p of xi log 1 by p of xi base 2. Now you know p of xi value and for all the 7 symbols. So please write down all the corresponding values and please calculate the entropy. Here the thing that you should remember is it's log 4 base 2. Okay, log 4 base 2. So this you can easily solve. Log 4 base 2, you can write 4 as 2 square. So power you can take outside the logarithm as a product. So log 2 base 2 is 1. So here you will get 3 log, because 8 you can write it as 2 cube. So log 2 cube base 2. So it is 3 log 2 base 2. So it will be 3. And here you will have log 2 power 4 base 2. So 4 you will get here. So finally you will get entropy H as 2.625 bits per message. Okay, and in this case they have given in the question that you will get the efficiency as 100%. What can be the reason and again? So in the question they have asked you that the code efficiency you will get it as 100%. You will get the code efficiency as 100%. What is the reason? The reason is that the entropy we obtained, so entropy as well as the average code word length is same. And you may get a doubt why I did not mention log m base 2. So L into log m base 2 we have to write actually, but here m is 2. M is 2. So because the reduction value is 2, so log 2 base 2 will be 1. So directly you can write it as h of x by L. H is 2.625 and L length is also 2.625. So that's why we obtain the efficiency as 100%. So the average information per symbol is equal to the average code word length. That's the reason the code efficiency is 100%. Please wait 1 second. See, even if you consider same example for Shannon-Fano and Huffman coding, you can be able to increase the efficiency by using the Huffman coding processor. Or else you can take one example and solve the same example using Huffman coding as well as Shannon-Fano encoding process, and you will get higher efficiency for Huffman coding, because there is no possibility of code word which is prefixed to the other, because here we'll use prefix free codes. So that's why the efficiency is high when compared to Shannon-Fano coding processor, and it is also stable. Okay. Okay, this is all about the Huffman coding. So what are the steps that you should follow? First step is represent the symbols in the order of decreasing probabilities. Okay. Second step is combine the last m number of terms. For example, m is 2, combine last 2 terms. If m is 3, combine last 3 terms. If last 2 terms are combined, assign 0 to the last but 1 term and 1 to the last term. If m is 3, assign -1 to the last but second term, and 0 to the last but 1 term and 1 to the last term. So like that you will combine, and this combined value is once again represented in the decreasing order probabilities. For example, if the newly combined value is same as some of the probabilities, this should be given priority. So this should be taken to the top position even when we have equal probabilities. Okay, but the whole should be in the decreasing order probability. Like that, the combining, assigning and relocating the probabilities in the decreasing order, the same process will continue till the reduction process consists of m number of messages. In this case, m is 2, so that's why we consider the reduction process till m is equal to 2. That is, still 2 probabilities remain in the reduction process. And at last you will assign 0 and 1. Because if you take a 0 and 1, if you combine these two, you will get it as 1. So the process will continue till the total probability leads to 1. Okay, so you need to assign 0 to the top one and 1 to the last probability, last symbol. Okay, and please ensure that during this reduction process, after each and every stage, you should reduce one symbol. In stage 1, you have 7 symbols. Stage 2, if you observe, you have reduced one symbol by this combining process. So, ante meeku S5 varke ravali table chart. And if you observe S3, you will get only up to S4. And in stage 4, we have to reduce one symbol. So, S3 varke meeku chart represent cheyali. Next in S5, stage 5, we will have only 3 probabilities or 3 symbols. So each and every stage, so upon increasing in each and every stage, we will have reduction in one symbol. So that's why Huffman coding will every time tell that it follows the reduction process. So it follows the reduction process by combining the last m number of probabilities, m number of symbol probabilities. Okay, so after completion of this whole process, what you need to do? You need to calculate the code words and its length. To calculate the code word for a particular symbol, follow the path in the forward direction and observe the assigned values anywhere if you find, and represent this code word in the reverse direction. So follow the path and observe the or else you can write the assigned values anywhere, and please represent the code word in the reverse, the order in the reverse direction to represent the code word. Okay, this is how you will get all the code words. After code word, you will calculate the code word length, and code word length into probability. Like that, you will add for all the particular symbols. So summation pk into the length of the symbol in bits. So you will get the average length After that, you will calculate the entropy. So entropy you can directly observe by using the probability column. So 0.25 log 0.25 base 2 plus 0.25 log 0.25 base 2 minus of, or else the easy procedure is 0.25 you can write as 1 by 4. Okay, 0.125 you can represent as 1 by 8 and 0.0625 you can represent as 1 by 16. You can use any procedure, but you should get the entropy as 2.2625. Answer should be right. So whatever the procedure you follow, you should get the proper answer. And code word efficiency is h by L into log m base 2. Here log m base 2 is 1. So directly I represented as h by L. So we obtain the efficiency as 100%. This is all about the Shannon-Fano coding method and Huffman coding approach. Okay. So these two approaches are very important for your examination. And out of these two, you will get one model. It's no doubt in that. Okay, the procedure is same. It's all both are entropy based techniques. And only difference is Shannon-Fano coding method relies on partitioning process, and our Huffman coding procedure relies on combining or reduction process. Okay, so with this we completed Shannon-Fano and Huffman coding procedure. So you can go through problems, more number of problems, but the procedure remains same, except the reduction value or partitioning value. So here Shannon states that, let us move to the Shannon's theorem. Here Shannon states that for a source of m equally likely messages, so let us move to the Shannon's theorem. Shannon states that for a source of m equally likely messages with m far greater than 1 generates an information rate capital R with a capacity of capital C, then the information rate capital R should be always less than or equal to the channel capacity. So what Shannon stated? Shannon, he individually stated that the information rate of the source, which consists of m equally likely messages, the information rate should be always less than or equal to the channel capacity, because the channel has a capacity of transmitting certain number of bits. Okay, our information rate, what is information rate? What is information rate? The units are bits per second. So the number of bits transmitted per second should be always less than or equal to the maximum capability of the channel. So the maximum capacity of channel capacity is capital C. So our channel has a capability of allowing only capital C bits per second. So our information rate should be always less than or equal to the channel capacity, because if you transmit more number of data, then can our channel allow that data? No. So that's why always information rate should be less than or equal to the channel capacity. So the units for information rate is bits per second, and at the same time the channel capacity units are also bits per second, because channel has a capacity of allowing only certain number of bits per second. So our information rate should be always less than or equal to the channel capacity. So maximum value of information rate should be equal to the channel capacity. It should not be, we should not go beyond that value, because channel cannot allow that many number of bits per second. Okay, so what is the Shannon's theorem? Shannon stated that for a source of m equally likely messages with m far greater than 1, okay, generates an information rate with a capacity of C, then the information rate should be always less than or equal to the channel capacity. Okay, so this is the Shannon's theorem. Next here you can see Shannon capacity theorem. See the second statement proof we will discuss in the module 6. Okay, in the next module we will discuss this proof, and you can say that this is Shannon-Hartley theorem. Okay, so this is Shannon's capacity theorem or Shannon-Hartley theorem. Okay. So here Shannon's capacity theorem or Shannon's Hartley theorem states the capacity of Gaussian channel for R less than or equal to C. So every time the information rate should be always less than or equal to the channel capacity. Every time the information rate should be always less than or equal to the channel capacity. And our Shannon's capacity or Shannon-Hartley theorem states the capacity of Gaussian channel as C is equal to bandwidth log 1 plus SNR base 2. So this Shannon-Hartley theorem we can prove it as a capacity of a Gaussian channel. Okay, capacity of Gaussian channel as bandwidth into log 1 plus SNR base 2, and this is valid only when R is less than or equal to C. Okay, this is valid only when it satisfies the Shannon's theorem. So Shannon's theorem is R is less than or equal to C, and our Shannon-Hartley theorem or Shannon's capacity theorem is bandwidth into log 1 plus SNR base 2. This is valid only when R is less than or equal to C. So please remember the Shannon's theorem so that you can continue with Shannon-Hartley theorem. So Shannon states that the information rate R is always less than or equal to the channel capacity, where the units are bits per second. And Shannon-Hartley theorem states the relation between the channel capacity, bandwidth and SNR as C is equal to bandwidth into log 1 plus SNR base 2. Here we are considering an analog channel which is a Gaussian channel. Okay, so every time we need to consider the distribution as Gaussian distribution because it will give the optimum result. So if you consider the channel as Gaussian distribution, the distribution as Gaussian distribution, then we'll get the optimum result. So that's the reason we will consider the channel distribution as always in the Gaussian form. Okay, this is all about the Shannon-Hartley theorem, and this is the Shannon's theorem, and the proof of this we can discuss in the module 6. Okay. With this we can complete our module 5. Okay, let us move to the module 6. So in this what you studied, we discussed the advantages of source coding, the two kinds of coding techniques, Shannon-Fano and Huffman coding. These two are the lossless compression techniques, and we calculated the efficiency for both the techniques, and the basic Shannon's theorem we discussed. Let us move to the module 6 where we will discuss the capacity of all the discrete channels as well as the capacity of Gaussian channel. So capacity of Gaussian channel is nothing but the Shannon-Hartley theorem. Okay, so we can discuss it in the module 6. With that module 6 we can finish our 4th chapter. Okay, I think this module is okay to everyone. Let us move to the module 6. Okay, here you can we'll discuss the capacity of discrete channels. So what is the capacity definition? Okay, and how this channel capacity is related to the mutual information as well as the information rate. See, the Shannon already stated, he stated the relation between the information rate and the channel capacity as R is less than or equal to C. Okay, that is stated by the Shannon. Now there exists another relation that specifies the channel capacity in terms of mutual information. Already we discussed the mutual information and we studied what is the importance of mutual information. So and average of mutual information and its some of the properties we studied in the module 4. What is mutual information? Any one of you, what is mutual information? Any one of the student, please tell me what is mutual information. So in this module, we'll discuss the capacity of discrete channels, the capacity of Gaussian channel, and the bandwidth SNR trade-off, which we have seen the equation in the earlier slide. Okay, now let us move to the concept of Shannon's theorem and the relation between channel capacity and mutual information. Now I request any one of the student to please define the mutual information I of xy. Actually, I of xy is the average of the mutual information. Please define the mutual information. Any one of you.
Difference between the two uncertainties due to P of xj and P of xj by yk.
Okay, very good. That is the mutual information of the transmitter. Okay, so it is the difference between the uncertainties of the priori probability, that is P of xj, and the posteriori probability P of xj by yk. So knowing yk, and you can say that it is I of xj minus I of xj by yk, where I of xj is minus log x, P of xj base 2 and I of xj by yk is minus log P of xj by yk base 2. Okay, that is the mutual information. It gives the information between the amount of data transmitted from source to the destination or the acknowledgement received from receiver to the transmitter. Okay, so once you know the mutual information, there exists a relation between the channel capacity and mutual information. Here I of xy is the average of mutual information. Now already I stated the first point. Shannon states that for a source of m equally likely messages with m far greater than 1 generates an information rate capital R with a capacity of C, then the information rate capital R is always should be always less than or equal to the channel capacity. So this is the Shannon's theorem. Now let us move to the relation between the channel capacity and the mutual information. So he also stated that the channel capacity, so channel capacity is defined as the maximum value of mutual information. Channel capacity is defined as the maximum value of mutual information. So the maximum amount of mutual information is generally defined as the channel capacity. So channel has a capability of allowing the maximum amount of mutual information, that may be from transmitter to receiver or receiver to transmitter. Okay, so what is the relation between the channel capacity and mutual information? C is equal to maximum of I of xy. Please remember this equation. First equation is R is less than or equal to C is Shannon's theorem. Okay, and in general the channel capacity is related to mutual information, as channel capacity is always equal to the maximum of the mutual information, the average of mutual information. So in terms of mathematical expression, capital C, so channel capacity is represented with the letter capital C. And already you know the information rate is represented with the letter capital R. So both have units of bits per second. And C is equal to maximum of I of xy. So channel capacity is the maximum of mutual information. Okay. So please remember this equation. Channel capacity is always the maximum of mutual information. So we calculated the mutual information for two channels. One is noise-free channel and other is independent channel. Okay. So how can you define the efficiency of a channel? Let us see. The efficiency of a channel is defined as the ratio of actual trans information, that is mutual information, to that of maximum trans information. So maximum that you can transfer the information is channel capacity, because even though how much information do you possess, the capacity of a channel should be satisfied. Then only our information can be transmitted. So until and unless the channel has a capacity to tolerate the amount of bits transmitted per second, we cannot allow like lot of information. Ratio of trans information to that of maximum of, for an independent channel, capacity C is equal to okay. So what is the efficiency? Efficiency of a channel is defined as the ratio of actual trans information, so transfer of information, that is I of xy, that's nothing but the mutual information, to the top maximum trans information. So maximum amount of transfer of information can be calculated by using the channel capacity. So efficiency is calculated as the ratio of actual trans information, that is mutual information, to the top maximum trans information, that is channel capacity. So in terms of mathematical representation, we can define eta. Eta as the efficiency. In terms of I of xy and channel capacity C, efficiency can be defined as eta is equal to I of xy divided by C, where I of xy represents the mutual information, average of mutual information, and C represents the channel capacity. So first equation is R is less than or equal to C, that is Shannon's theorem. And after that, Shannon also stated the channel capacity as the maximum of mutual information, that is maximum of I of xy. See the module 4 and 5, we calculated the entropies, and using entropies like marginal, joint and conditional entropies, we calculated the mutual information. Because I of xy is h of x minus h of x by y, or h of y minus h of y by x, or h of x plus h of y minus h of xy. So using the three relations, you can calculate or interrelate the mutual information with the 5 kinds of entropies, and you can calculate that. Okay, and now in this module, we'll calculate the channel capacity by using the mutual information. So we'll calculate the mutual information, and the maximum of that will give you the channel capacity. Okay, in this module, we'll calculate the channel capacity of various discrete channels and the Gaussian channel. The capacity of Gaussian channel is nothing but the Shannon-Hartley theorem, which is C is equal to bandwidth log 1 plus SNR base 2. So that relation is the capacity of Gaussian channel. And in the same manner, we will calculate the capacity of various discrete channels. Okay, so that's about the module 6. So efficiency, already I told you, it is defined as a ratio of actual trans information to that of maximum of trans information. Trans information represents the transfer of information. So I of x comma y divided by C, where I of xy represents the mutual information, divided by the maximum mutual information is channel capacity. So C. This is efficiency. And the redundancy is generally defined as 1 minus efficiency. So 1 minus eta is I of x of I divided by C. So if you want to calculate the efficiency, take I of xy by c. And if you want redundancy, take 1 minus eta. So it will be 1 minus I of xy divided by c. I of xy divided by c. So these two are if you want to calculate the efficiency given the I of xy and c, directly you can calculate eta and the redundancy factor. Okay, now let us move to two kinds of channels what we have discussed already. So already the fourth property and fifth property of mutual information, I already discussed the mutual information of noise free channel. Can any one of you tell me the fourth property of mutual information? I told you the mutual information of noise free channel is, what is the mutual information of noise free channel? Any one of you? Fourth property of mutual information. I told you the mutual information of noise free channel. Any one of you? Please respond.
I of xy is equals to h of x is equals to h of y.
Okay, because h of y by x or h of x by y, conditional entropies are 0 for a noise free channel. Okay, so for a noise free channel you will get the matrix as unity diagonal matrix. So the h of x by y, that is conditional entropy of transmitter knowing receiver, or h of y by x, conditional entropy knowing of receiver knowing the transmitter, is 0. So because for a noise free channel h of y by x or h of x by y is 0, I of xy can be calculated as either h of x minus h of x by y or h of y minus h of y by x. So for a noise free channel h of x by y and h of y by x are 0. So you can write I of xy as directly h of x or h of y. So for a noise free channel, because already I calculated the mutual information, directly I substituted here. So this is from the fourth property of mutual information. So, but what is the relation between channel capacity and mutual information? Here in the second equation you can see channel capacity is maximum of mutual information. For the noise free channel, mutual information is either h of x or h of y. Now can any one of you tell me what is the maximum value of entropy for m equally likely messages of transmitter h of x or n equally likely messages of the receiver section y? Any one of you? I think we studied the sixth property of entropy. What is the sixth property of entropy? For m equally likely messages, okay, here we are considering two sections. One is the transmitter and other is the receiver. For m equally likely messages, the entropy, so maximum entropy occurs at P is equal to 1 by m is how much? What is the maximum entropy for m equally likely messages that occurs at P is equal to 1 by m? Or what is the maximum entropy of n equally likely messages that occurs at P is equal to 1 by n? So what is the maximum entropy value? We studied it in the property 6 of entropy. Any one of you? Please tell me what is the maximum value of maximum entropy? Please some of you respond. Log m base 2. Okay. Oh,
Base 2 bits per message.
bits per message. That is for the transmitter. Receiver, come on. For example, if I consider n equally likely messages and at P is equal to 1 by n, what is the maximum entropy? h of y. Log n base 2 bits per message. Okay, very good. So channel capacity is maximum of either h of x or h of y. So from the sixth property of entropy, maximum value of entropy occurs at P is equal to 1 by m for the transmitter section, or probability equal to 1 by n for the receiver section. Okay, this is for m equally likely messages for transmitter or n equally likely messages for the receiver. If so, then the maximum entropy is log m base 2. Okay, if we have m equally likely messages. If we have n equally likely messages, it is log n base 2. So because the channel capacity is the maximum of mutual information, but for a noise-free channel, mutual information is either h of x or h of y, because conditional entropies are 0. So maximum of h of x, so nothing but maximum entropy. So maximum entropy for m equally likely messages occur at P is equal to 1 by m is log m base 2. And if for receiver, if the probability, so if you consider n equally likely messages with n far greater than 1, that occurs at P is equal to 1 by n is log n base 2. So that's why for a noise free channel, channel capacity is either log m base 2 or log n base 2. This is the first property of channel capacity. Remember, this is the first property. So first channel that we discussed is a noise free channel. So because the mutual information is either h of x or h of y, maximum of that value is either log m base 2 or log n base 2. Log m base 2 for the transmitter and log n base 2 for the receiver. Next, in the fifth property of mutual information, I told you for an independent channel, what is the mutual information? How much we obtained? Any other student? For an independent channel, what is the value of mutual information? We studied it as a fifth property of mutual information. Any one of you please tell me, for an independent channel, what is the mutual information? Any other student please respond. So almost 60 students are there. Any one of you please respond. What is the mutual information for an independent channel?
Zero, ma'am. I of
Zero.
x equals to 0.
Because here in the case of independent channel, the h of x is either h of x by y or h of y is h of y by x. So marginal entropy is equal to conditional entropy వస్తుంది మనకి. So that's why I of xy is 0. So maximum of 0 will be 0 only. So for an independent channel, because the mutual information is 0. Why the mutual information is 0? Because in the case of independent channel, we considered joint probability as the product of individual probabilities. Okay, and if you replace the mutual information, you will get h of x as directly h of x by y or h of y as h of y by x. But mutual information is the difference between h of x and h of x by y or h of y and h of y by x. So if you do like that, you will get mutual information as 0. But the channel capacity is defined as the maximum of mutual information. So that's why you will get maximum of mutual information. So maximum of 0. Okay, so that's a constant value. So channel capacity is also 0. So for an independent channel, please remember that independent, what it means? Nowhere the transmitter and receiver are related to each other. So for an independent channel, no data from the transmitter is sent to the receiver. So then that you can say that is an independent channel. So I am speaking to you and you 60 students are listening. So it's a channel. There is a path because you are listening during some app via the channel. So other students are there which are not linked to the corresponding group. Then I can say that is an independent channel. then what is the channel capacity is 0 at that time because there is no path. Okay, so but for a dependent channel, we'll have some channel capacity and that we can calculate as maximum of mutual information. So because for a noise free channel, we'll get maximum value and it is log m base 2 or log n base 2. But for an independent channel, the mutual information is 0 because no information is transmitted from transmitter to receiver or no acknowledgement is sent back from receiver to the transmitter. So mutual information is 0. So our channel capacity is also 0 because maximum of I of xy. So for an independent channel, channel capacity is 0. Okay, please remember these 2 points as the properties of channel capacity. So in the exams, if they ask you define channel capacity and list the properties of channel capacity ante em chestaru, first channel capacity you should define as the maximum of mutual information and it is always greater than or equal to the information rate. So you can define the channel capacity in 2 manners, by using Shannon's theorem and by using the maximum of mutual information. So first define this by using this expression and you tell that this is valid only when the information rate is less than or equal to the channel capacity. So first you should write these 2 points and then you can jump to the properties directly. First property is for a noise free channel, channel capacity is 0. Sorry, it is log m base 2 or log n base 2 because I of xy is either h of x or h of y. And for an independent channel, because mutual information is 0, channel capacity is also 0. Please list these 2 points as the properties and we can discuss the remaining properties in the tomorrow's class. Okay, so that we can finish our 4th chapter. So any doubts in the today's class? Any doubts?